In the standard normal distribution, the bell is in the middle, and the mean and the median, as well as the mode of the distribution, are all the same. Many everyday things happen, such as the heights of people within cultures, take the shape of the bell curve, and in statistics, it is often assumed that the characteristics of the population being studied takes the shape of the bell curve. However, this is not always the case. When distributions have a bell that is not centered, this called a skewed distribution. In skewed distribution, there are a large number of values to one end of the range than the other, and fewer on the other. The type of skewness is based on which side of the curve the tail is. If the tail goes off to the right, the curve has a positive skew, or if the tail goes off to the left, if the curve has a negative skew. When dealing with outliers in data, there are two ways of doing so: trimming and Windsorizing. Trimming is finding the values different from the group, like the anomalies, and removing them from the dataset to create a more rounded set of data. Performing trimming on a small set of data might not work, however, as when the researcher has a small set of data, it reduces the sample size even more, and in a quantitative data collection, you would typically go for a larger sample size, so it would only work with like big projects. And Windsorizing is when you take the outlying results and turn them into the closest result. So, for example, if you have a score of 14 and then an extra score of 29, or if you say you have a data set and all the numbers are between 10 and 14, and then there's 29, the 29 would then turn into a 14, and it happens for smaller numbers as well. So, say there was a 3 as well in there, the 3 would turn into a 10. This allows the researchers which have smaller ranges in their data set to keep all their data, but not have like outliers in their data as well. Descriptive statistics are used to describe the findings in a numerical form at basic level. The different options for presenting data are central tendency, which is the mean, median, and mode, standard deviation, interquartile range, and dispersion. Central tendency is a single number data that represents the data set. This includes the mean, median, and mode. The mean is all the numbers in the data set added up, then divided by the amount of participants in the data set. So with this example of standing vertical jump, the mean is 37. The median is all the numbers lined out in numerical order or rank order, and then the middle value is the median. So again, with this example, 40.5 will be the median. This because there are two middle numbers in the set, and there's an even amount, so it's just in between the two values. And the mode is the most common number in the data set. So with this example, again, it's 51. Dispersion relates to the spread of data. This is the range, standard deviation, and interquartile range. Standard deviation is worked out using the sum, the square root of the sum of x minus the mean of the data squared over n plus 1, and that's how the standard deviation is calculated. And the range is the difference from the highest value to the lowest. Again, and then the interquartile range is the middle 50% of the data, and this is worked out by splitting the data up into 4 equal quarters, and from there you can take away the top, say if it's like, and you take away the upper quarter and the lower quarter, which give you the middle half of the data. The interquartile range is the difference between the third and first quartiles, and it is a measure of dispersion. Running through the Pearson test for correlation, first you have to get the number of participants, which is 8 in this example. Then find the sum of x squared, y squared, and xy. Then you need to take the sum of x and square it, and the sum of y and square it. And after this, you have to put the sums of x and y into the formula and it gives you the calculated R value, which seen on screen is 0.47. This then gets put into a table of critical values where you can see there's the degrees of freedom down in the first column, and then the level of significance for the two-tailed test on the top row. The degrees of freedom is figured out by the number of participants minus 2. So for this example, again, is 6. And you get the calculated R value, which before was 0.47. And you find, so you get the degrees of freedom, then go along to the level of significance, and it gives you in the table 0.7067. And because that is above 0.05 as our p-value, it shows that our R-value, it shows there isn't a significant difference in the data. For Spearman's rank order test, it's used when you have data that is ordinal or ranked, and if you want to investigate a relationship between those two sets of data, you would aim to have collections in the data set, but usually over 15 or more is valid. And as you can see, for this data set, you have to find the sum of D, the difference between the ranks, and the difference between the ranks squared. Then you put it into the equation shown at the bottom of the screen, and it gives you 0.4. And again, you put this into the table of critical values, and it will show you if there's a significant difference or not. And we get a critical value of 0.74, and it does show that there's a significant difference. Next is the independent t-test, and this would be used when you have two separate groups of participants and you're trying to discover if the mean scores of the groups can be classed as significantly different. Again, for this, you're going to want to find the means of both groups and then the standard deviations, and you can put them into the independent t-test formula, which I have done on screen, and it gives you a score of 1.31. Then looking again in the table of critical values, for this one, the degrees of freedom is figured out by adding both the amounts of participants from both tests and then minusing 2, so it gives us 18 this time. And we can go down to 0.5 again, and it shows that we have a 2.101 critical value. And because this is and then this shows there is a significant difference in the data. And finally, we've got a dependent t-test or a paired t-test, and this is used if to see if there's a significant difference between the two tests or the two sets of related scores. For example, with the example of the pre and post training jump height. And again, you go through and find the sum of data set 1, sum of data set 2, the difference between them, and the difference between them squared. Put them in the formula, and for this we got an answer of 3.2. And then again, you put this into the critical values table to see if there's a significant difference or not. And for us, for this dependent t-test critical value, there is a significant difference. And finally, a decision tree is used to determine the correct test that needs to be done when conducting some research. As you can see, there are routes to take if you're using different types of data. There are 3 types of tests that I will not be using in this assignment, but will run through why you would use them. These are the Wilcoxon matched paired signed ranks, Mann-Whitney U-test, and the chi-squared test. The Wilcoxon matched paired test requires ordinal data, and to have differences between related rankings. It's a non-parametric statistical hypothesis test used to compare 2 related samples, matched samples, or repeated measures on a single sample to assess whether their population mean ranks differ. When using the Mann-Whitney U-test, the data will have to be ordinal and have differences between unrelated rankings of 2 groups. The Mann-Whitney U-test is used to compare differences between 2 independent groups when the dependent variable is either ordinal or continuous, but not normally distributed. And this test is often considered the non-parametric alternative to the independent t-test, although it's not always the case. And finally is the chi-squared test. You use this if you're working with nominal data and there are differences among frequency counts in the data. The chi-squared test is used to determine whether there is a significant difference between the expected frequencies and the observed frequencies in one or more categories. The chi-squared test can be used to attempt rejection of the null hypothesis that the data, and has to be that the data is independent. All these different tests are on the tree, so you can test for different types of things. For example, if you want to find difference or correlation in tests or means, you can use the same test. And they would give different answers, which is why the tree shows which test you need to do for what data you're using.